In this video, I want to talk about the different representations for a system or an event. Moving between and translating representations is something that every scientist and engineer needs to know how to do. So let's do an example here, and I'll start with a verbal representation of an event. And when I mean verbal, I mean to describe a system in words, whether it is in fact verbal, speaking, or written. So the verbal representation is I have an animal, and it has a constant acceleration. I'm not going to write full sentences to save time, though usually your, say, problems in your book would be verbal representation of a system, and usually written in full sentences. Okay, constant acceleration. And it covers 70 meters in 7 seconds. Its speed at the second point is 15 meters per second. So this is a verbal representation of a system, and let's say I want to describe everything as that I can about this system. But there's a verbal description. So if I want to understand this problem more, I might move to what I'll call a pictorial representation. Now, there may be an infinite number of representations. I'm going to only talk about, say, 6 here, the ones that will commonly be used in this course to be able to solve problems. And there isn't any standard definition for these terms as well, but I'm giving them words that are descriptive of the type of representation that they are. So a pictorial representation is, as well as I can draw, a picture of the event. So here is a very poorly drawn stick animal, and so it's running and it's accelerating, so it might sort of this from here to here, and then maybe here at a later time. And I'm saying that, okay, well, it gets between these, this covers 70 meters in 7 seconds. And so I've drawn a pictorial representation of what's happening. I might say, okay, at the end it has 15 meters per second. So what good is a pictorial representation? A pictorial representation is good to help you visualize the problem. In any problem, you want to have a clear idea in your head of what's happening or what's going to happen as good as it can. And drawing a pictorial representation can help that. Okay, so let's say now I'm going to move on to what I'll call a schematic. I'm not so interested in solving the problem here or talking so much about the problem as much as talking about the different representations of it. So here, let me go to a schematic representation. What, in my mind, the difference between a schematic and a pictorial representation is where in the pictorial, I'm just looking for a picture to be able to visualize it. A schematic now is more quantitative. I'm going to have a coordinate system. I'm going to have an axis. So I need to identify a 0 of my coordinate system, x, and which direction is positive x-axis. I'm going to now represent my object, in this case, by a particle. And so now here's my t is equal to 0, and then at later t is equal to 7. It's at 70 meters. It has a velocity of 15 meters per second, and then I might give it a little, a couple points to show in my mind that it's accelerating. And so I've now simplified my pictorial representation to I've got a particle instead of a picture, as well as a coordinate system with a direction, a positive axis. And so this is going to help me now quantify my motion. So that's sort of what I call a schematic representation. In most of the problems that we do, pictorial representations now and then will be useful. You will almost always need some form of schematic representation, especially for any type of problem, especially in kinematics. And so this is a particularly important one, where you establish your coordinate system, establish your zero, etc. All right, so if that's a schematic representation, now let me move to something else we'll call a graphical representation. And so a graphical representation is just that. I'm representing the quantities of interest in graphs. So what are my quantities of interest in kinematics? They're the acceleration, the velocity, and the position. So why don't I go ahead and do that? I'll start with the acceleration. So I'm going to draw a graph of the acceleration. The acceleration is a function of time, and it's a vector function of time, but I'm going to just I'm going to graph its magnitude. The sign determines the direction of the vector. And so I, in fact, don't know what the acceleration is. I do know it's constant. So I'm going to say a sub 0, or a naught, is my constant acceleration. And so my graph of the constant, my graphical representation of my constant acceleration would look like a flat straight line at a value of a naught, which is at the moment yet unknown. Fine, that's my graphical representation. Let me try a graphical representation of my velocity. Again, I'm not saying that this is necessarily the best way to solve this particular problem. I'm just doing examples of representations. All right, so here's going to be a graphical representation of my velocity as a function of time. Well, I know that it has some final velocity, which is equal to 15. This is in meters per second. If I want to give these units, this would be meters per second squared. Time is in seconds. And it's constant acceleration, so I know that the velocity is increasing linearly. It had some initial velocity, which is unknown. I'm going to say that the time was equal to 0 at the point when it started. I got that from my schematic diagram. And so at some later time, it has, in fact, the later time is at 7 seconds later. It has some final velocity, which is equal to 15 meters per second. And so I can draw a straight line here because I know, because the acceleration is constant, the velocity is increasing linearly. So I don't know what my initial velocity is yet, just like I didn't know the acceleration. So that would be a graphical representation of the velocity as a function of time. So now finally I might draw my my position as a function of time, which I'll say is in meters. And now here I'm given my coordinate system. The way I set up my coordinate system in my schematic, the first I defined when it crossed the first point to be x is equal to 0. So it starts here, and it ends 70 meters later in position at some point later, which is 7 seconds. And since the velocity is increasing linearly, I know the position is increasing quadratically. It may not be a good good parabola, but it's a curved function that goes from 0 up to 70 in 7 seconds. And so here are 3 graphical representations of the quantities of interest, the position, the velocity, and the acceleration. So just for fun, let's see if we can't work on the problem using our graphical representation, since that's not something that students necessarily do a lot. They like to go to the mathematical representation. So let's work on the graphical for a bit. So we know that the area under the the area under the velocity curve gives us the displacement. And we know that the displacement from 0 to 7 seconds was 70 meters. So that means the area under the velocity curve is in fact 70 meters. So what does that give us some relationship between these parameters? What is the area under the velocity curve? Well, that's easy to calculate. I've got a rectangle here and then a triangle. And so the area of this rectangle is 7 seconds. So this dimension here, the area under this curve, has units here. It's important to keep those units. So 7 seconds times the height of this rectangle is our initial velocity, which is in meters per second. It's unknown. Plus the area now of this triangle. Area of a triangle is 1/2 the base, which is 7 seconds, times the height here, which is the difference between the final velocity and the initial velocity. And so that's 15. I know the final velocity minus the initial velocity. So this is the area underneath this curve, the sum of the rectangle times the triangle. This is in velocities, meters per second. The seconds cancel. So my result is in meters. Well, that's good. And we know that I sort of ran out of space here to the right. So we know that the area under that curve is equal to 70 meters, the total displacement of the position. Okay, so now I can solve this. This is just an equation. My only unknown here is v sub I. So I can in fact solve this for v sub I. I get 7 v sub I. I'm going to leave off my units now. I know everything is in meters. 7 v sub I plus, multiply this through, 52.5 minus 3.5 v sub I is equal to 70. This is 3.5 times 15, 52.5. And so this gives me that 3.5 VI, 7 minus 3.5 is equal to 70 minus 52.5, which is 17.5. And VI is equal to 5. And this is all in SI, so I know that this is meters per second. So just using my graphical representation, I was able to come up with something I didn't know before, which was the initial velocity, the velocity when it crossed sort of the first point in time. In fact, now that I have the initial velocity, I can calculate the acceleration. Because it's a constant acceleration, the acceleration is given by the slope of this line. And that slope, then, the acceleration, is the slope of a straight line, delta v over delta t. And what that slope is 15 minus 5 divided by 7 minus 0, or 10/7 meters per second squared. So here, just for an example, we were able to use a graphical representation to essentially solve for unknowns in the problem. We have our initial velocity and, in fact, our acceleration. All right, so let's move on. We now look at a graphical representation. In fact, we used it a little bit. Now let's go on to mathematical representation. Now, if I hadn't solved it yet, I might bring a mathematical representation of the problem to be kinematics equations, relate 2 points in time, do some algebra. For this one, since we already have the answer, we don't need to go through all that. I can just write down the mathematical representation of this problem of all of our quantities of interest. Our acceleration as a function of time is 10/7 meters per second squared. Our velocity as a function of time is equal to 5 plus 10/7 t, and this is in meters per second. Our mathematical description is the equation that gives us that line. And then our position as a function of time is then 5t plus 5/7 t squared. And this is now in meters. This is the mathematical expression that gives us this line, this curve in this graph. And if you're not immediately jump to this conclusion and see how I got these equations, that's not so important at this point. Remember, I'm not. The most important thing is to show the different representations. And so this is what I would call now a mathematical representation of the original event. It's a series of equations for our quantities of interest: position, velocity, acceleration. All right. And it's not even necessarily the only type of mathematical representation, but this is sort of a common mathematical representation. Okay. So in fact, finally, just to give us another one, I might look at a tabular representation. Now, a tabular representation might say, okay, so for different times, I'll have positions, velocities, and accelerations. And I say, well, at 0, our time, our position was 0, our velocity was 5, and our acceleration was 10/7. I should put, this is meters per second, meters per second squared. This is in seconds. And then I could fill out a table however much I wanted. Maybe for each second I might do that. At t is equal to 7 seconds, I might have 70 as a position, 15, and then 10/7 it doesn't change. So when would you ever want a tabular representation? Well, it depends. Sometimes you would need that to communicate to others the position or these quantities at particular points in time. So that brings up an important point. So going between all of these representations is important for everyone who's pursuing a career in science and engineering. And it's not just to solve problems, but it also is important in communicating the way, communicating your solution to problems. Once you solve it, you may end up communicating the information mathematically, or you might communicate it in graphs, or you might communicate it in tabular form. So being familiar with lots of different representations and being able to translate between them is an important skill that we'll develop in this course.